Welcome in the second part of Visual Crash Studio training session, recorded for Impact Design Europe. In this part, I will continue with more practical information. I will show you how to develop simple model in a reasonably short amount of time and how to extract results after calculation. Let's go back for a second to the beginning of the whole presentation. Now, after the first part, when we learned how to define the cross-sectional properties, we can focus on the 3D structure development and simulation settings. The Visual Crash Studio is equipped with a tool which facilitates creation of the model using FE data, provided in form of LS-DYNA key file. Usually, the tool, which is called Create Superbeam from FE part, requires to follow procedure described in a few steps. This enables to create Superbeam semi-automatically. Why semi-automatically? You will learn in a few seconds. Basically, when we have already imported data, we need to hide all not necessary parts. That means the parts which will be not included in the cross sections. This is the first step. After selecting the tool, we need to indicate the part which will be the base for our new Superbeam element. This is the step number 2. White knots should appear on a selected element. Now we need to define the direction of centrifugal axis of Superbeam element. To do that, we need to select two nodes. This is the step number 3. The fourth step is the selection of the element between previously selected nodes. The element indicates the position of the cross-section to extract. Once the section is positioned, we need to follow instructions from the output window and press C button on the keyboard. Our Superbeam element should appear on the screen. This is the step number 5. But in step number 6, we need to modify the cross-section to fulfill the requirements of macro elements methodology. And this explains why I called the process of the Superbeam creation semi-automatic. This especially concerns the cross-section with more complex geometry and the one which includes the connections between structural elements. We already know that the cross-section editor has a number of tools which enable to create and modify geometry of the cross-section. Accept the properties to change and displayed in the properties window, we can add points, change their position, create and modify new plate element. We can also create the connections between plates. The 7th step of the procedure comes when all modifications are completed. We need to clean the cross-section using the tool which is called Remove Not Connected Points. Select the cross-section and click right mouse button to remove points. In the end, we have to calculate the cross-section. Sometimes the Superbeam element may require modifications of orientation in 3D space. This is caused by the fact that SBE is positioned with respect to basic shape before modifications. After words of introduction, it's time to go to the beginning of the bumper tutorial. To import the data, we go to File menu, Import, FE part, LS-DYNA. The window where we select the file and check the consistency of the unit system will appear on the screen. After that, we select Import. Subsequently, another window where we select the parts to import will appear on the screen. In case of our file, we select all the components and click Import. Our imported data should appear on the screen. To make operations of Superbeam creation more convenient, we select all the elements, and we need to change the node size in the Properties window of all selected components. Now let's play for a second with the management of data. We need to group the components to avoid the collection of parts which doesn't stay in the range of our interest while the creation of the new cross-section. We select the parts which reflect the geometry of the crash box and front part of the frame at the right hand side of the structure. We group them using the Group tool. New group will appear in the Explorer window. Now we can change the visibility options in the Properties window. We hide grouped elements. Now we start to build our 3D structure. Select the Create Superbeam from FE Part tool. Please notice that tips and hints will appear in the output window below. Now follow the instructions presented a few slides before. Select the front bumper element and indicate two nodes to define the axis of the Superbeam element. We select first node, we select second node, and now we have to indicate the position of the cross section to extract. We use the C button to create Superbeam element. We assume that our structure is symmetrical. Therefore, to speed up the process of creation of the Superbeam element model, let's create the right hand side of the bumper. That's how the structure should look like after creation of the Superbeam model at the right hand side of the front bumper. Now we have to do the modifications at the cross-sectional level. To indicate the cross-section of each Superbeam element, we can easily do that by selecting the Superbeam element and click right mouse button. We select the cross-section, which should be also selected in the Solution Explorer tree. We enter the cross-section from the Solution Explorer tree. Now we have to do the modifications at the cross-sectional level. As we see, the original geometry does not coincide with the geometry created automatically by Visual Crest Studio. We have to move points and create the new plate. To move points, I select the Move Point tool and I move the points. Now I need to create new plate. To do that, I choose the Select tool and I indicate the plate at the end of the cross section. To create new plates, I use the Divide Plate tool. This tool divides the plate into two plates. After all, I move the middle point of the divided plate. Now I can calculate the cross section. Now I repeat the cross-sectional procedures for all created cross sections. When all modifications for all cross sections are completed, I can remove not connected points using Remove Not Connected Point tool available from the context menu after clicking the right mouse button. I can also calculate all the cross sections. After calculation of cross sections, we see that the structure does not coincide with the original data. Something's wrong? Not. We need only to modify the orientation vector of each Superbeam element. To change the orientation vector in our case, we need to select all superbeam elements and go to second section of properties. We go to orientation vector and enter values for x, y, and z coordinates. It's worth to say that orientation vector values should not coincide with the orientation of the superbeam in global coordinate system. That means if we have a beam oriented in y direction in global coordinate system, the component of the vector in y direction should be equal 0. Now we can create the left-hand side of the bumper. To do that, we need to create the group first. We select all the superbeam elements and create new group, as it was in case of the crash box and front frame of the structure before. Then we need to clone the elements. We select the group in Solution Explorer tree and click the clone. The copy of group will appear in the Solution Explorer tree. The newly created elements coincide with the original ones, therefore we will not be able to see them in 3D window. Now we have to mirror the group to the left-hand side of the structure. To mirror our structure, we select our group which was copied before and we select the mirror tool. Then we have to define the reference plane and click OK. Our structure will appear on the screen. Now it's time to connect our structure together. As we see, there is a gap between the left-hand side and right-hand side of our structure. We will start from changing the coordinate of the middle point. We select the knot on the right-hand side of the structure and we change the y coordinate to 0. Now we have to connect our structure together. Therefore we will use the substitute knot tool. At the beginning we have to follow the instructions from the output window below. First we have to select the superbeam element. When we select the superbeam element, the start knot will be marked in the frame, as it is shown in the picture. Now we have to select the new knot of our beam. The new knot is the one in which we change the coordinates to 0. When we change the knot or create new knots, we have to remember that standing alone knots should be removed. Front structure of the bumper is created. We can add it to the group and change the visibility options. Now we can create the superbeam element which represents the crash box in macro element model. As you may notice, for the convenience I changed the visibility options. The FE bumper is hidden, superbeam's visibility was switched to wireframe. To create the crash box, we follow the well-known instructions. Select two nodes, which gives the direction of the centrifugal axis of superbeam element and the element between those two nodes. When our superbeam is created, I go to cross-sectional properties. I select the superbeam and I open the cross-section. I need to modify the cross-section geometry and add some additional elements. These elements are the connections. To create the connections, I select the Create Connection tool. Then I select the first plate of the first connection and the second plate of the connection. I repeat this for the second connection. When modifications are done, I can calculate the cross-section. Don't forget about removing not connected points from the cross-section. The geometry is ready. Now I have to adjust the position of beam in the 3D space. When we look closer to our geometry, we see that the superbeam element does not coincide with the original data. To move superbeam element, we will use Move Node tool. When we select the node to move, we can also use the number of options, which are described in the output window below. We select the node and we lock the movement in Y direction. Now when we move the node, our structure looks much better than before. The remaining part is a frame. We will use only a fragment of frame. We create the superbeam element using create superbeam element from FE part. We modify and calculate the cross section. We adjust the position of superbeam element in the 3D space. Now we will connect Crashbox with frame using substitute node tool. We will use different settings for the substitute node than before. I want to connect these two elements using a rigid offset. This means that original position of superbeam elements will not be changed. The only difference is that two superbeams will be connected with rigid link. The rigid link is not an additional element. It is related with the superbeam which node has been already changed. We can change the offset at each end of the superbeam. We can change this property in the properties window after selection of superbeam. As we assume that our structure is symmetrical, we can reflect our structure with respect to XZ plane. We add the superbeam elements to group. We clone our structure and reflect it using a mirror tool. When all the superbeam elements are ready, we have to connect our Crashbox with the front bumper. We use the substitute node tool. We do the same for the right hand side of the structure. And now we can clean our model. We can remove number of unused elements from our model. We can remove characteristics, materials, cross-sections, points at the cross-section level, but in our case the most important is remove standing alone nodes. We select this option and click OK. Our bumper structure is ready. Now we have to define the barrier. We will start from creating the node on which the barrier will be based. We select the Create Node tool and we type in the coordinates of the node. And we click Create. When we enter coordinates x equals 10, y equals 0, z equals 470, the new node should appear in front of the bumper structure. Now we have to define the barrier itself. In fact, the barrier is a rigid body which is based on the node which we already created. To create the rigid box, we select Create Rigid Box tool and indicate the node. Now I have to adjust the size of our barrier. To do that, I select the rigid box and I go to Geometrical Properties. I go to Dimensions field and I define the values for x, y and z. In Visual Crash Studio, the contact algorithm between elements is simplified. Therefore, I need to create an additional element to define the contact between them. In case of our bumper, I need to define the spheres at the front nodes of the bumper, and to do that I turn off the display of all superbeam elements and I indicate all nodes in the front. When all nodes are selected, I go to Contact Impact Settings in the Property window and I select Create Contact Sphere to True. The number of spheres will be created automatically. When additional elements are created, I need to define the contact between them and the barrier. To do that, I need to create the contact pairs. Each contact pair contains two elements. The first object is sphere and the second is a barrier, our rigid box. We need to define the contact pair for each sphere and the barrier. In our sample model, there should be 13 number of contact pair elements. When we select the contact pair, we can notice that in Property window, we can change the properties of each contact pair. Now we need to define the boundary conditions of our simulation. We will start from the barrier. We want our barrier to be locked in all degrees of freedom. We select the base node of the barrier and we go to Properties, which is called Kinematic Constraints and Concentrated Loadings. We select the kinematic constraints, and when we do that, there should appear a gray rectangle at the right hand side of this property. We click on this rectangle and kinematic constraints window should appear on the screen. We select Add. New interval should appear in kinematic constraints window. We go to Fix tab and we select the Elapse checkbox. This means that the constraints will be valid for whole simulation time. When setup is ready and we select Apply button, our node should be displayed as follows. Now we have to define the boundary conditions at the end nodes of our structure. We select the end nodes and we go to Kinematic Constraints and Concentrated Loadings. We repeat the procedure as it was in case of the barrier node. Accept the boundary conditions, we have to define the concentrated mass at the end nodes of the structure. To create the concentrated mass, we go to Properties of the node and we enter the value for concentrated mass. In our case, it will be 550 kilograms for each node. I need to also define the initial conditions for our simulation. To do that, I select all the nodes except the node of the barrier. I need to go to Kinematic Constraints and Concentrated Loadings and find the velocity in x direction. When I enter this property, the kinematic constraint window should appear on the screen. I select Add and then I go to tab Constant Velocity. I need to enter the value of velocity in meters per second. Notice that in this time I need to set the end time to 0, the same as it is at the start time. This means the initial velocity. Our simulation model is ready. Now I need to go to the simulation settings. To do that, I select the most top element in Solution Explorer window and I go to Properties, which is called the time stepping routine. I need to define the elapsed time, which in our case will be 80 milliseconds, and I need to define time increment and time step critical. In case of time increment, it will be 0.005. In case of time step critical, it will be 0.008. Now I can calculate our solution. I select Calculate Solution from the toolbar. The processing unit will be open. And I select Start. When calculations are started, the processing unit shows number of messages. The processing unit checks the model consistency and also indicates the stability criteria. After calculation, it also shows the elapsed time of calculation. When calculation is completed, we can close the processing unit and run the visualization of our simulation. We can extract the data using the chart wizard. Select the chart wizard on the toolbar. When the chart wizard is displayed, we select the elements from which we want to extract the results. For instance, we select nodes and the super beams. And we select the values which stay in the range of our interest. Originally, the values are displayed in a function of time. We can change the time to any other value displayed in a window below the graph. This slide presents the values which can be displayed in a chart wizard. We can display values from the solution, from group, from superbeam elements, and from nodes. When we see the visualization of our simulation, we may notice that some superbeam elements change the color. This color corresponds to the state of the superbeam element. The dark gray macro elements stay in an elastic range. The dark green elements have reached the limit load. The dark yellow, golden elements correspond to the state of the post-collapse range. The red elements are in deep collapse region. When we use the chart wizard, we can create number of graphs. These graphs can be improved using filters. We've got number of filters implemented in Visual Crash Studio. The second part of Visual Crash Studio training session is completed. Now we know how to create a simple structure, how to define boundary conditions and initial conditions, how to set the simulation, and how to extract the results from calculated model. Thank you for your attention. I hope the information included in the presentation were helpful. If you have any questions, please don't hesitate to write on support@impactdesign.pl.